Carbon is one of the most familiar elements on Earth. It's in pencil graphite, charcoal, diamonds, and even the cells in our bodies. For centuries, humans have burned it, mined it, and built civilizations around it. There's nothing exotic about it at first glance, but something extraordinary happens when carbon is engineered at the nanoscale, at dimensions measured in billions of a meter. At that scale, carbon transforms into materials with properties that almost sound impossible. It can become stronger than steel, conduct electricity nearly as well as copper, and contain surface area so massive that a single gram can unfold into the equivalent of an entire basketball court. And according to a growing body of research, these tiny carbon structures may help solve one of the biggest technological challenges in the 21st century: how to store energy better. The papers in this collection focus on a central question: can we build an energy storage device that combines the strength of both batteries and capacitors? Right now, batteries and capacitors have trade-offs. Capacitors work differently. They store energy electrostatically by accumulating charge on a surface instead of rearranging chemical bonds. That means they can charge and discharge incredibly fast and survive hundreds of thousands of cycles. But traditional capacitors store very little energy. Batteries, like lithium-ion cells in phones and electric cars, can store large amounts of energy through chemical reactions. Given the high energy density, meaning they last a long time, but charging them takes time, and the materials slowly degrade with every single cycle. Supercapacitors sit in between these two technologies. They can charge in seconds, release power almost instantaneously, and last far longer than batteries. They're already used in things like regenerative braking systems, in buses and cranes, where rapid bursts of energy matter. The problem is energy density. A lithium-ion battery might store over 200 watt-hours per kilogram, while the conventional supercapacitors often only store 5 to 10. Closing that gap has become one of the most important engineering problems in energy storage research, and carbon nanomaterials are emerging as one of the most promising solutions. One of the most famous of these materials is graphene. Graphene is astonishingly simple, just a single layer of carbon atoms arranged in a hexagonal lattice, one atom thick. But despite that simplicity, graphene has some of the most extreme properties ever measured in a material. It's highly strong, highly conductive, and theoretically has the largest surface area of any known material. For supercapacitors, that huge surface area matters because energy is stored directly on the electrode surface. In theory, graphene should make the perfect supercapacitor electrode. But reality turns out to be more complicated. Graphene sheets naturally stick together because of weak molecular forces called van der Waals interactions. When they stick, they start behaving more like ordinary graphite, and much of the usable surface area disappears. Researchers discovered something surprising while trying to solve this problem. Defects actually help. Normally, defects in materials are considered flaws, but in graphene, carefully engineered defects can prevent sheets from stacking too tightly, keep space for ions to move through, and even improve the material's ability to store charge. One study found that defect-engineered graphene increased capacitance by about 250% beyond what the theory originally predicted. So in this field, perfection isn't always the goal. Controlled imperfection can produce better performance. Another major carbon nanomaterial is the carbon nanotube. You can think of a nanotube as a graphene sheet rolled into a tiny cylinder. These structures have remarkable electrical properties. Depending on how they're rolled, nanotubes can behave like either metals or semiconductors. For energy storage, metallic nanotubes are especially useful because they can store charge and conduct electricity effectively. Unlike flat graphene sheets, nanotube also resist collapsing into stacked layers. Networks of tangled nanotubes naturally create porous, three-dimensional structures that allow for ions to move quickly through the material. The combination of conductivity and open architecture makes them ideal for high-power supercapacitors. Research also combining nanocarbons with entirely different materials to create hybrid systems. One particularly advanced example involves carbon nanofibers coated with boron-doped diamond. This idea almost sounds futuristic, combining the high surface area of carbon nanofibers with the extreme chemical stability of a diamond. The resulting electrodes can behave partly like supercapacitors and partly like batteries, storing energy through both electrostatic charge and fast chemical reactions. That hybrid behavior is important because it helps bridge the divide between high-power capacitors and high-energy batteries. Another direction in the field involves building nanocarbons from polymers. Instead of starting with graphite and breaking it down, researchers design special polymers and heat them in oxygen-free environments. The non-carbon components burn away, leaving carefully engineered carbon structures behind. What makes this approach so effective is control. The original polymer determines final carbon shape, porosity, defect density, and even chemical composition. For example, polymers containing nitrogen produce nitrogen-doped carbons, which improve charge storage and catalytic activity. This means that carbon nanomaterials are no longer viewed as naturally fixed substances, researchers can increasingly treat them as designable architectures where nearly every property can be tuned. And as the field has advanced, scientists have started realizing that nanoscale confinement itself changes the laws of behavior for materials. One of the most remarkable examples involves water. Normally, water is not considered an ideal electrolyte for supercapacitors because it breaks down voltages at about 1.23 volts. But researchers recently created devices where water was confined inside channels only 1 nanometer wide between graphene and clay layers. And at that scale, water behaves differently. Its hydrogen bonding changes, its dielectric properties shift, and proton transport becomes unusually fast. Most surprisingly, the confined water remains stable at voltages far beyond what bulk water normally allows. As a result, supercapacitor with a competitive energy density and an extremely long life cycle, all using water as the electrolyte. This discovery highlights one of the deepest ideas running through the entire field. At the nanoscale, familiar materials stop behaving in familiar ways. Water becomes something new. Carbon becomes something entirely different, and physics itself starts to look different. Researchers are also pushing toward miniaturization. As electronics become smaller, wearable devices, sensors, embedded systems, energy storage needs to shrink too. One study explored porous silicon with titanium nitride using techniques already common in semiconductor manufacturing. The goal is to create in-chip supercapacitors built directly into electronic hardware rather than attached to separate components. That could fundamentally change how electronics are designed. Across all these studies, another consistent theme appears. Hybrid materials outperform single materials. Graphene provides enormous surface area but tends to restack. Nanotubes provide conductivity and structural stability, and polymer-derived carbon can offer chemical flexibility. By combining them into nanocomposites, researchers can compensate for the weaknesses of each individual material. In many cases, the interfaces between materials become just as important as when the materials themselves. At these scales, the boundary between two structures can dominate how electrons and ions move throughout the system. And that leads to the most important conclusions in this entire body of work. The main challenge is no longer discovering exotic new materials, it's learning how to precisely engineer architectures. The theoretical performance already exists. The difficulty is assembling these nanostructures in ways that preserve their extraordinary properties at practical scales. And scalability remains the biggest unsolved problem. Many of the best performing devices are still laboratory demonstrations, and the manufacturing methods are often slow, expensive, and difficult to reproduce industrially. So while the science is still advancing rapidly, translating these breakthroughs into mass-produced technologies is still an open challenge. Still, the trajectory is clear. Over the past decade, carbon-based supercapacitors have improved dramatically in energy density, stability, voltage range, and cycle life. And the broader lesson may be even more important than any single device. Carbon at the nanoscale isn't just a better version of an old material. It's something new entirely.